part 8.3, Simple Recurrence Relations. In this video, I want to show you how to solve a very special type of recurrence relations. Very simple. Yeah. But you need to use some special technique. Yeah. All right, so let us look at our Tower of Hanoi problem, efficiency analysis. How many disk moves do we need to solve the problem with n disks? Yeah. All right. Count the number of basic operations. What is the basic operation? Yeah. Very simple. Yeah, we can see it easily. Move a disk from one peg to another one. That's the basic operation. One move. Yeah. So here we define the count function C of n. To move n disks from the first peg to the last peg, we need C of n moves. Yeah. All right. Let us derive the recurrence relation. C of n equals, so how do we represent C of n? It is this, because we need to solve the problem of n-1 disks twice. So then we need to use C of n-1 twice, 2 times. After that, we need to move the bottom disk, so another one move, so plus 1. Yeah. So this is our recurrence relation. The question is how to solve it. It is very simple, right? But how to solve it? You need to use some special technique. Now, here, let me show you how to use some special math technique to solve it. Yeah. All right. We need an initial condition. Yeah. When we have a recurrence relation, we need an initial condition. Yeah, that's simple. When you move one disk, only one move. Yeah. One disk problem, one move. Yeah. All right, to solve the recurrence relation, we need to use some math operations. Yeah. But here, there is one basic idea we need to use, or basic method we need to do, transform the formula. We need to change the form of the formula. Yeah. After we change the form, the problem becomes easier. Yeah. So let me show you how to change the form. Yeah. All right, solve the recurrence relation. How to transform the formula. Yeah. All right, here, so let me give you the reason. Because when we change the formula, we need to have some direction to go, right? Where to go? Here, let me give you the direction. The direction is explore the similarity in structure. Similarity in structure. Yeah, let me explain. So what's the meaning of that? Yeah. When you look at this formula, left-hand side, right-hand side, they have different mathematical structures, right? Yeah. Because the right-hand side, you have plus 1. Left-hand side, you don't have plus 1. So they have different structures. Yeah. How to explore similarity of structures, how to make both sides have the similar structure. That's the direction we want to go. All right, so there is one simple technique. We add 1 both sides, because here you have plus 1, right? In order to make the left-hand side plus 1, we need to add 1, okay? Yeah, C of n plus 1. But right-hand side, it becomes plus 2. Although we have plus 2, look at this 2 coefficient in front of C of n minus 1. So we have a common factor 2. We can factor that 2 out. After factorization, you can see inside the parenthesis, it is a C of n minus 1 plus 1, right? Plus 1. You can see plus 1 both sides, C of n plus 1, C of n minus 1 plus 1, do they have the similar structure? Yes, that's the similar structure. That is the important structure we want to explore. Because with this kind of similar structure, we can introduce a new function to represent that structure. So we introduce a new function d of n that equals c of n plus 1. Because after we define this new function d of n, we can make our original recurrence relation simpler. Yeah? Because the right-hand side, it becomes 2 times d of n minus 1. Yeah. So after simplification, we have a simpler recurrence relation. Simpler than the original one, right? Because that plus 1 is gone. Okay? Yeah. So with this new one, so we update the base equation. D of 1 equals 2 this time. Yeah, because D of 1 equals C of 1 plus 1 by the definition of D function. So that is 2. All right. Yeah. So then we can do iterations. Yeah. 2 times d of n minus 1, can we apply the recurrence relation another time? Yeah. So we replace d of n minus 1 by 2 times d of n minus 2. All right. Then combine 2 steps. We have 2 squared times d of n minus 2. Yeah. But we need to keep going, right? Step by iteration, until we reach the end. But the question is, how do we keep track of all the intermediate steps? How do we keep track of everything for the intermediate steps without loss? Yeah, because we could get a loss, right? Yeah. So we need to use some special technique to guide us, along the same direction until we reach the end. That idea I used once before in our string matching problem. I used that. You remember? String matching problem. How do we figure out the last location, the starting location of the last m substrate, right? At that place, I use a new idea, invariant idea. Here, I use that idea another time, invariant idea. What is the invariant? When we do iteration by iteration. Here, our observation is the exponent of power of 2 plus the problem size n minus 2, it is a constant. 2 plus n minus 2 equals n, right? That sum is a constant when we do iterations. Yeah. 2 to the first, that 1 plus the size number of the d function n minus 1, 1 plus n minus 1, constant n. All right. When we do the iterations, we always have this rule. All right. Until we reach the last step, power of 2, exponent number n minus 1, the size number is 1. N minus 1 plus 1 equals n. In this way, we can keep track of all the intermediate steps. All right. So at the end, because d of 1 equals 2, 2 times 2 to the n minus 1 power, so we get d of n equals 2 to the n. And the last step, we go back to the c function, we get c of n equals 2 to the n minus 1. So that is our solution. Yeah. Think about, try to understand how do we solve the simple recurrence relation. Yeah. It is very simple, but you can see we use some special idea and a special technique, and it is very effective. Yeah. All right, so let me stop video 8.3 right here.